Welcome to the geometry portion of the 3D Conduction tutorial. First, we must open up the geometry file. We will select the closest desired length unit, which is micrometer. Now, we have 4 parallel planes of which our materials sit on. We can either create 4 planes and model them as a positive extrude, or easier, we can just create 2 planes and extrude in the positive z direction and the negative z direction. So I will place the 2 planes at the 2 borders, the silicon and silicon dioxide border, and the platinum and the water border. These 2 planes are therefore the thickness of the silicon dioxide and the platinum combined, which is 400 nanometers. So we shall create a new plane that is based off of the xy plane and transform it in the positive z direction by 400 nanometers, or 0.4 micrometers. Now we need to create the silicon layer. This is a simple enough layer in that it is a large rectangle. We will put the border of the micrometer bridge and the tab at x equals 0, just to simplify things. So for the silicon, we must create a rectangle across that boundary. So the dimensions of the left side will be the length of the micrometer bridge, which is at 100 microns. Excuse me, micrometers. The length to the right side of the axis will be the same length as the tab, which is 250 micrometers. The height will be the height of the tab, 250 micrometers. Zooming out to get a proper view of this. There we go. Now we select the sketch and extrude it as a frozen material. The difference between add material and add frozen is that when you add material, it combines with whatever is already existing in your sketch. When you add frozen, it remains separate from everything. So we want to extrude it in the reverse direction, which is in our case the negative z, as a depth of 300 micrometers, which is the depth of the silicon. When we generate this, we can see that we have a large block of silicon. Now let us hide the sketch so it does not interfere with our next sketch, and create a new sketch. This will be the tab and the micrometer bridge of the silicon dioxide. First, the tab, and then the rectangle for the bridge. The bridge's height, or width, is at 1.5 micrometers, and its length is again 100 micrometers. Tab, 250 and 250. There we go. Now we want to extrude this as a frozen material in the positive z direction, or the normal direction. It is 200 nanometers thick, so by 0.2 micrometers. And we generate it. Notice that we now have 3 bodies. When you have a separation in the sketch, as shown by this line right here, it will automatically create bodies that are separate from each other when you select Add Frozen. This is actually advantageous to what we want. It will help with our meshing in the future, and will help us separate the boundary conditions for the platinum. For only the bridge, for only this micrometer bridge, will be producing heat and not the tab. Let us make sure to name these bodies. This is the silicon. This is the silicon dioxide, the tab portion. And this is the silicon dioxide, the bridge portion. The platinum layer will be the same dimensions as the silicon dioxide layer. Having created a copy, but just on the different plane, we now extrude it again, but instead we extrude it in the reverse direction. Remember to add the frozen. It is also 200 nanometers thick, so we do not need to change that. Now we can take a closer look at it. We can see that there are two layers. This is the platinum and this is the silicon dioxide. If they have merged together, then you forgot to add frozen. Now we need to add the water. We know that water, being a liquid, will fill in all available gaps, so we need to fill in this rectangle with water. So, we add in a new sketch. With a new sketch, we simply draw a rectangle and center it along the vertical line, making sure not to center it on the horizontal line. With the dimensions, you can see that the horizontal here will again be 100 micrometers. The vertical between the bottom and the horizontal is the width of the micrometer bridge, which is 1.5 micrometers, and the height of the entire object to the axis is 250. Since this is on plane 4, we need to extrude it in the same layers as the platinum and the silicon dioxide. So, in this case, that means extruding it in the negative z direction, or reversed. Again, add as a frozen. And the combined thickness of the platinum and silicon dioxide is 400 nanometers. Alright, let us remember to name all of the objects. This is the platinum tab. This is the platinum bridge. And this is the water interior. Now we need to add in the exterior water. So let us hide the sketch and create a new one. Again, this is a simple rectangle which will cover all of the known material in the z direction. So it will be dimensioned exactly the same as the silicon. (100 micrometers to the left of the axis, 250 to the right of the axis, and 250 above the axis. Now comes the interesting part. We know that the water is a stationary object that is at least a few millimeters thick. However, we also know that the bridge is only a few micrometers. So, if we were to model all of the millimeters of water are object would contain far too many elements to be computed in a proper fashion. We also suspect that not all of the water is being used in this heat transfer process. The depth is an unknown, so we need to make it a design parameter. In order to do this, we behave as normal. We extrude as a frozen in the normal direction, but then we click this box here, which makes the depth of the water a parameter that can be changed. We need to name this, so let us just name it water depth. And it needs a initial depth. We know that 0.4 micrometers is way too small. So to change the values of the parameters, we click on parameters, and we can simply rewrite it here. So let us put it at 500 micrometers. As you can see, it changes. And then we need to generate. We will now name the water. And here comes an important part. We must shift-click all of these and form a part out of them. Creating a part out of all the bodies is important, as it links together the contact regions between the bodies and the border of the mesh. This concludes the geometry portion of the 3D conduction tutorial.